So now we get into the proof. We've done the lemma above, and getting back to the main theorem, we divide it into cases. The base cases are for atomic sentences. The first sort of atomic sentence is where our sentence phi is the equation of some two terms, and we suppose that the structure M satisfies phi with arguments a bar. Recall that that's our set of assumptions, and what we are trying to get to is the claim that the structure N also satisfies phi with argument, the mapping of a bar due to the isomorphism. J is again the isomorphism in this proof. So we assume that phi in this case is an equation of two terms, and that the structure M satisfies phi with arguments a bar. Now, the very definition of a structure satisfying an equation of terms is for the function determined by those terms to map a bar to the same element. You'd have to go back to the definition of satisfaction and terms as functions and so on to fully unpack that, but it is what that expression means in this case. Now, from this we can apply the mapping to the two elements here, right? This is an element out of the domain, this is the same element out of the domain, so if I apply the mapping, those will again be the same. In fact, I wrote that this equation is justifiable due to injectivity, but in fact, that's not really true. This is merely due to the fact that J is a function. And therefore it maps any one thing to precisely one thing. So really this equation is just due to the fact that J is a function. I get this equation. Now on both sides, right, identifying that expression with this other one here, we know that these are equal due to the sort of structure-preserving property of the map J. Likewise, this is equal to this, again, by the structure-preserving feature of map J. And there we have it. All of these things are equal, and the equality of these two things is what meets the definition of structure N satisfying phi on argument J of a bar. And that is what we wanted to prove. So we could repeat the proof for the other atomic, the other base case where phi is an expression of a relation on some terms. The argument goes very much the same way. And then we get to the inductive case where we suppose that phi is, in one case, equal to negation psi, and in that case, the structure satisfies phi on a bar if it does not satisfy the underlying sentence on a bar, and due to the isomorphism, we have that structure N must also not satisfy, or sorry, not due to the isomorphism, due to the inductive argument, right? We now have a less complex sentence because we've peeled off a negation. So because we have a less complex sentence, the inductive hypothesis kicks in. We know that we can transfer from M to N and get that N does not satisfy psi, and therefore by definition of phi as the negation of it, and by definition of satisfaction, we get that N does satisfy phi. And so on, the remaining parts of the proof go in basically the same way.